Good evening. Welcome to People's University Livestream. We are back this week with the last 2 weeks. We've talked about science as a school of thought, right? As a philosophy, and all the issues that have come with it throughout the history of the development of science. But this week we are going to start actual hard science with chemistry and the fundamentals of chemistry. And I will introduce our guest, our instructor, in just a moment. I wanted to mention that on Tuesday we'll be talking about some of the lesser known legends of Wheeling from the segregated era of Jim Crow, African American leaders in the community, 9 different people. That'll be Tuesday at noon to begin Black History Month. And our next class in this series, next Thursday on February 4, Erin will be back with us to talk about the work she does, the work she's done for many years now, combating antibiotic resistant bacteria. So that'll be fascinating as well. Now, tonight, if you comment, question, like, or share, or anything like that, if I see that you've engaged in this program, you will be entered into a drawing to win, first of all, the Chemistry of Beer pint glass, which I know is highly coveted. And Erin will show you a couple things that she's also added to the giveaway. Go ahead, Erin. Can you hear me?
I can hear you. Thanks, Sean. So yes, I got into the spirit of gift giving, and I have a trilogy of chemistry books that actually are really terrific for the scientist and the non-scientist alike. The first of which is The Elements. It's a very large book, by the way, but it's filled with pictures and facts and anecdotes about all your favorite elements and even ones that aren't your favorites. Feel a little like Van White. The second book is Molecules, and so of course molecules are made of elements, and so this takes you through different molecules, and again, pictures, stories, uses, etc. And then finally, last but not least, we have Reactions. So molecules interact and they react, and this is a really fascinating book filled with lots of stories about how molecules do just that.
They're beautiful books. I want them. But I can't win them. But you can. So just ask a question, and well, let's get on with it. Let me introduce our instructor this evening. Erin Duffy is a PhD, has 17 plus years of drug discovery and problem solving experience in the antibiotic arena. She earned her BS at Wheeling College. It's Wheeling Jesuit College, maybe at the time, and her doctorate at Yale University. She's now Chief of Research and Development at Carbex at Boston University. Here is Erin Duffy.
Okay, hello everybody. So I'm going to take you through a presentation of the fundamentals of chemistry. Got to be honest with you, haven't really thought about many of these fundamentals in a long time. I've been a practitioner of chemistry in the pharmaceutical industry doing drug discovery, and certainly that's chemistry as well. But as we get more and more applied, sometimes we forget to take a step back and think about the fundamentals. So I'm going to share my screen and hope this works. Let's see. Okay, so I'm hoping everyone can see this. I can't see myself, but I'm counting on Sean to text me if for some reason you cannot see them. So Sean gave this title, The Fundamentals of Chemistry. Maybe the subtitle is, or what a chemist turned drug discoverer likes to focus on for 20 minutes. I'll say that this presentation was derived from a tutorial that was created by Bill Jorgensen at Yale. Bill actually is a professor of chemistry, and many of you will also know him as my husband. Okay, so I wanted to, before I got into stories of chemistry, I wanted to follow on the discussion that we had last week. So last week we had 4 women scientists who engaged in a conversation among ourselves and with you about many, many things, the scientific method, but also we touched on women in science and our journeys through that. And I think a lot of us want to feel, and certainly historically it has been true, that women have not been prominent scientists, particularly in the physical sciences. And so maybe you know this and maybe you don't, but in the last 2 years, we've had women win the Nobel Prize in chemistry. So this year, 2 women shown on the left here of your screen, Emmanuelle Charpentier and Jennifer Doudna, co-won the Nobel Prize for their development of a method for genome editing, and this is otherwise known as CRISPR. So, pretty terrific story. These are young women, very bright. This technology is taking off in many arenas, and so very, very exciting. In 2018, Frances Arnold, shown on your right, won the Nobel Prize in Chemistry for the directed evolution of enzymes. So she was half of the prize, and the other half went to 2 guys for phage display. But the women definitely showing up in chemistry. And I should point out that Frances Arnold is now on the Biden Science and Technology team. So when Sean asked me to do this, I was wondering, what am I going to do? How am I going to pitch this? What am I going to cover? And this was right around Christmas time, and I had given this book written by Jennifer Doudna, which is on the topic of gene editing. I think a lot of ethical questions around that. And I gave it to a neighbor of mine for Christmas. And so one day we were walking around the neighborhood with our dogs, and he said, hey, got some questions for you. Number 1, and this, by the way, is a CEO of a major car conglomerate, so, not a dumb guy. And he says, can you remind me what an atom is? And how's an atom related to a molecule? And when does chemistry become biology? And I thought, these are great questions. This is what I'm going to focus on. So what we're not going to do today, we're not going to balance equations. I'm not going to tell you 8 billion different reactions by the name, which is usually some white guy who created the reaction. We're not going to do any of that. It's not going to be memorizing. We're just going to learn some fundamentals and talk about these key aspects. Okay, so let's get to the heart of the matter. What is matter? Well, matter is anything that has a volume and a mass. And there are 2 broad categories of matter: substances and mixtures. Okay, so underlying all of this is the atom. The atom is the fundamental unit in chemistry. I saw a cute little comment before we started about someone eating electrons, which I thought was amusing. In any event, an atom is comprised of an inner core, which is called the nucleus. And in that core are protons, which are charged, and neutrons, which are not, hence the name. They are surrounded by this fast-moving cloud of electrons, which are negatively charged. And so, this is not an animated picture, but those red lines with the red dots are meant to connote the fast-moving cloud of electrons. It is the case that the number of protons equals the number of electrons in an atom, and that number is a signature of the type of atom. And we'll talk about types of atoms in a second. The other thing to note is that atoms do have a mass, and that mass is expressed in atomic units, which are called daltons. And just to give you a sense, obviously you can't see an atom with the naked eye, but 1 dalton is 1.67 times 10 to the minus 24 grams. So that's like really, 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 really small. So these are some familiar atoms, I hope. On the top left is hydrogen. You have 1 electron and 1 proton. Carbon, on the top right, you have 6 protons and 6 neutrons in the nucleus, and then 6 electrons floating around. Nitrogen has 7 protons, neutrons, and electrons. And oxygen has 8 protons, neutrons, and electrons. But you know, today there are 118 different elements, and we're going to talk about this, but an element is basically an atom or more than one atom, and we'll talk about that in a second. But this is the periodic table. There's hydrogen up in the far right. You see carbon, nitrogen, and oxygen, which we just talked about. One click down and to the right. But these are all the different elements. And this chart is just filled with information that we're not going to go over necessarily, but you know, there are lots of images of the World Wide Web, but I want to point out a few things to you. In every one of these boxes, so this is the atomic symbol for hydrogen, H. Above it is the atomic number. The name is below it, which hydrogen's fine, but when you get down here to something like ytterbium, YB, that one doesn't really fall off the tongue, so that's why they tell you what it is there. Anyway, below that, you have the atomic weight or mass, and then below that, the number of electrons per shell. And so the shell is important. We're not going to talk about this much, but there's a sort of inner shell of electrons and then an outer shell, and it's the outer shell that's available for interactions and reactions. So first question, are atoms elements? And the answer to that is yes. So on the left, here are atoms of an element. So these are so-called monoatomic elements, things like neon, silver, gold. Then you have molecules of an element. And so these are diatomic or polyatomic elements. So examples would be hydrogen. Hydrogen runs around as H2. Oxygen runs around as O2. Actually, sometimes also as O3, which is ozone, but there's a debate about whether you call that an element or an allotrope, so we're not going to get into that crazy debate. Fluorine runs around as F2. Some elements run around polyatomic, so phosphorus you see here is P4, sulfur S8. Well, so how does a compound figure into all of this? Okay, so we have the elements, we already talked, the atoms of the element, the molecules of an element. And the other thing I should point out is molecules of an element are always consisting of only one atom. You really, okay, I'm gonna do this, okay. And they cannot be broken down by chemical means. They can be nuclear means to break them apart, but not chemical means. Compounds of elements consist of more than one type of atom. So some examples that you know, water, H2O. Here we have ethanol, which is CH3, CH2OH. So 2 carbons, 6 hydrogens and 1 oxygen. And molecules or compounds can be broken down into simpler substances by chemical means. Okay, so a little bit more on substances. So substances exhibit characteristic properties, things like melting point, boiling point, solubility, density, but these do not depend on their origins. What do I mean by that? Well, if you went out and took water from a well, or you went into the laboratory and made water by combining hydrogen and oxygen, the water from the well, after you purify it, would be the same as the water you made in the lab. Substances may consist of neutral molecules, so again, things like we've talked about, hydrogen, water, and these are formed by electrons sharing in a covalent bond. But they may also be salts, so sodium chloride table salt is probably the most common of these, and these are formed through what's called an ionic bond, and the reason it's made that is there's this very strong electrostatic attraction from the charges, plus on the sodium, minus on the chloride. Okay, so then what about those mixtures? What's different about mixtures? Well, mixtures are really any number of substances. So anything to the left could be in a mixture. So you could have some ethanol in there, you could have some hydrogen in there, you could have some gold in there. These are not chemically bonded, and a mixture does not have unique properties. Okay, so we're going to talk a little bit about organic chemistry. I was joking last week, if you were here, not really joking, but just sort of maybe emoting about it. So the number of times I've gone to a medical doctor, and just as he or she is about to write a script for me for some sort of medication, he or she will say, when learning I'm a chemist, oh boy, I hated organic chemistry. And I think, oh brother, what do you think those molecules that you're writing for me are? We're going to talk about that in a few minutes. So maybe you know this and maybe you don't, but the origins of organic chemistry go back to the 18th and 19th centuries. And where organic chemistry really derived from was the study of compounds that could be obtained from living organisms. And these were deemed organic. And furthermore, they were imbued with what was called a vital force. And so these were very different from those inorganic molecules. Well, during these studies, there were a few interesting things that were noted. First of all, organic compounds always have carbon and hydrogen. They often contain many other elements as well. And so you'll see oxygen, sulfur, phosphorus, halogens. What are halogens? Halogens are things like fluorine, chlorine, bromine, iodine, and many others. The other thing that they learned was that identical compounds can be made in nature and in the laboratory. That was a pretty big shocker. We're going to talk about that in a moment. And it turns out that that's important because once they demonstrated that you could make organic compounds in the laboratory, that really opened up the world to a massive diversity of organic compounds that could be made to determine their usefulness. And you know, we just think for a second here about the pharmaceutical industry. If we didn't have synthetically made organic chemistry compounds, a lot of the drugs that you probably take chronically wouldn't be available. The other thing that's important, and this gets to that question of when does chemistry become biology, is that the so-called molecules of life, DNA, RNA, and proteins, they're just big organic molecules. And we'll look at some of those later. So this breakthrough about that you could actually make organic compounds in the lab, there's a lot of debate around who was the first to break through, but you know, many people think that this is true. Okay, so urea was identified as an organic compound found in urine, and this was done during the study of organic molecules from organs. But in 1828, this German scientist actually conducted the chemical synthesis of urea in the lab using inorganic starting materials. And so you see the reaction down here on the bottom. So this is lead, Pb is for lead. So this is lead cyanate plus ammonia and a little water. And this is what's called a double displacement reaction. And so you get lead hydroxide, and importantly, you get ammonium cyanate. But ammonium cyanate breaks down into ammonia and then cyanic acid. And this then rearranges to nothing other than urea. And we'll look at the structure of urea in a minute. And so, you know, this definitely, there was no white woman in the lab in 1828 to be shocked by this revelation, but certainly this was a revelation nevertheless. But that, as I said, really unlocked the value of what you could do with organic molecules to solve problems that we encounter. And so you think about here, just a slide of the small molecules, novel small molecules made in the lab that were approved in 2019 by the Food and Drug Administration. Now, this just happens to be in the area of oncology. And so you see 8 different molecules here, again, all created in the laboratory. And they have utility in different types of cancers. You see here, urothelial carcinoma, prostate cancer, lymphomas, etc., multiple myelomas. So all of these made by hands in the lab as drugs that can be used to cure people of cancer. Okay, so let's talk a little bit about bonds. This isn't a segment on financial investing, so, please don't take any advice there. Okay, we're going to talk about covalent bonds for a moment, and I'm going to focus on carbon just to make it simple here. Carbon likes to make 4 bonds. Why? I told you there were 6 electrons and 6 protons and 6 neutrons in carbon. Well, 4 of those 6 electrons are available on the outer shell to interact and react. Covalent bonds hold atoms together. They can be of many kinds. So you can have a single bond, which is when 2 electrons are shared between 2 atoms. So here's an example, methane. So again, carbon likes to make 4 bonds. Here's 4 different bonds, each to a hydrogen. And so the hydrogen is bringing an electron and the carbon is bringing an electron. And so carbon has 4 available, therefore it gets 4 hydrogens. Ethane, so ethane, there are 2 carbons in ethane, and so ethane, the carbon is sharing 1 bond with the carbon, and then the other 3 are for the hydrogens. Covalent bonds also come in the form of double bonds, and there 4 electrons are shared between 2 atoms. So here you have carbon, carbon liking to have 4 total bonds, so 2 of them are being shared between the carbons, and that leaves 2 bonds available for the hydrogens. So we go from ethane to ethylene or ethene. And then finally, you can have triple bonds, and this, of course, is where then 6 electrons are shared between 2 atoms. Okay, so here we have our 2 stars of the show in our 2 carbon atoms. They're triply bonded, so each has 1 open electron for hydrogen. And so this is ethyne or acetylene. So the distribution of bonds influences the shape and the properties of molecules. Okay, so we have our 3 molecules here, ethane, ethylene, and ethyne or acetylene. But that's in stick figures drawn as 2 dimensions. But if you actually put them in 3 dimensions, molecules do have shape. And if I could spin these around, it'd be even better. But you can see the projections. So they have a shape to them. And the single bond is, has a bigger shape and envelope to it. The double bond renders a flat molecule with some protrusions on the side. And the triple bond, this is just a molecular rod. But these configurations and these shapes affect properties like, for instance, the boiling points. So you can see here the boiling point of ethane is at the whopping minus 89 degrees Celsius, which for those of you who don't work in that system, it's about minus 128 Fahrenheit. But when you go from ethane to ethylene, your boiling point decreases even further to minus 103.7 Celsius. But it's not just that the heaviest molecule has the highest boiling point, because in fact, there's more that has to do with shape as well and charge. And so here, ethyne or ethylene or ethyne or acetylene comes back down to minus 84 Celsius. So compounds can also form rings. So I'm going to stick with carbon here for a minute. So here are our 2 molecules, cyclohexane and benzene. So I'm just showing them without their hydrogens for a minute. Each has 6 carbon atoms. Are they the same? Well, obviously they're not, because you see I have these lines drawn here, but what does that mean? Okay, so cyclohexane, again, carbon likes to have 4 bonds. So all of a sudden you see each one of these carbons has 2 hydrogens and it's connected to 2 other carbons. Whereas benzene, because it has this structure of a hybrid of single and double bonds, ends up having 1 hydrogen per carbon because carbon is participating in 3 bonds or 2 bonds, 1 double and 1 single with other carbons. Okay, well, this has a pretty dramatic impact on shape. And so here is 1 conformation of cyclohexane. This is a so-called chair conformation for obvious reasons. So again, you can see a real interesting shape here, whereas benzene is flat. And if you look at a space filling model, which really then gives you the sense of these electrons running around, you can see that benzene shape just has, a big cloud here, but again, a very flat surface. And you can see now the protrusions of the hydrogens from the scaffold on the cyclohexane. So very different structures, different molecular envelopes. And this, of course, has an impact as well on properties. And so here I'm showing you aqueous solubility. This is, how soluble these molecules are in water. And so you can see here at room temperature, so 25 degrees Celsius is about 77 degrees Fahrenheit. The solubility of cyclohexane is 55 milligrams per liter, but it's a whopping 1,790 milligrams per liter for benzene. So these bonding characteristics have an impact on how the molecule presents itself and then how it acts in terms of its properties. Well, this shouldn't really shock us. So if you think about people for a second, stick figures are a pretty poor representation of people. But so here's a stick figure of a man. Let's call him George. But does that stick figure represent all these Georges? So my favorite here, of course, is George Clooney. I mean, I would never get George Clooney out of this George. Another actor, George Costanza, again, very different from Clooney. Down here in the political arena, we have George Washington, pretty different character from these two guys, very serious too. And also in the political arena, we have two different Georges, George Sr., George Jr. Well, over here, we have some entertainers, George Harrison. We have George Benson, George Balanchine, and yes, Boy George. So this stick figure is meant to represent all these different men who happen to be named George, very different shapes, sizes, colors, talents, etc. So you might be asking, well, how do you know that the molecules look like that? How do you know that that cyclohexane looks like a chair and that the benzene looks like just a big, like, pie? Well, again, it's important to realize, I said it before, that compounds are also really small. So the typical length of our carbon-hydrogen bond is just about an angstrom. Typical length of a carbon-carbon bond is about 1.5 angstroms. And so you can see this is a vanishingly small inch. But there are experimental methods, and I'm sure you've heard of them, like X-ray crystallography, which uses X-rays here. It goes through a screen, hits the molecule, creates a pattern, and then that pattern, all those dots, tell you something about the orientation of the atoms in that molecule, and you can use software to then deduce the structure. You can also use electrons to do the same thing. So other molecules, just to finish this story up here, other molecules, of course, are built not just carbon, hydrogen, as we said. So again, back to our favorite atoms here for a minute, nitrogen. Well, nitrogen likes to form 3 bonds because it has 5 total. It has 5 total electrons in the outside. It likes to keep 2 to itself and 2 inside. And so it likes to make 3 bonds. And so here's ammonia. Here's methylamine. So just replacing one of those hydrogens with a nitrogen. And then adding the methyl group here. Here's an imine. So nitrogens can participate in double bonds. And here's a nitrile, also called the cyano group. So now you have a triple bond. Oxygen, by comparison, likes to form 2 bonds. And so you see here a lot of molecules you know well. Here's water. Here's methanol, so alcohols. Here's ketones. So an example of a ketone is acetone. Acetone, what is acetone? Well, it's a solvent, and certainly the ladies among us will recognize it as pretty strong solvent to take off fingernail polish, but used for many other things. Acetic acid, basically vinegar. And esters, so these are molecules that are often used in fragrances and used as flavors. Here's urea. Remember, we talked about the synthesis of urea. This is what it looks like in stick figure form. And then finally, amides. And we're going to come back to amides because amides are incredibly useful building blocks for the molecules of life. Okay, so let's talk a little bit about chemical reactions. So what is a chemical reaction? Well, it involves the change of one or more substances, so molecules, elements, compounds, into another substance. There can be multiple reactants, so things that go together, and products, things that are made. And so here's an example where you're going to, you're going to brominate methane, and so you end up with methyl bromide and HBr. Now, these reactions can often be helped by catalysts. So for instance, in this case, you could speed up this reaction by using heat or by applying light. And catalysts generally help to lower the barrier from getting from reactants over an energy hump to products. So it lowers that hump. Okay, another type of reaction is a change of state of a substance or a mixture. So generally, this involves a change in heat content between reactants and products. And so here, if you burn methane in air, you end up, of course, with CO2, carbon dioxide, water, and heat. And it might be interesting for you to know, and of course, this is the basis of heating your home with natural gas, that almost 14,000 calories of heat, not here, apologize for that typo, are given off for each gram of methane. 1 calorie is enough heat to raise the temperature of 1 gram of water by 1 degree Celsius at 15 degrees or 59 degrees Fahrenheit. That's a lot. So that's again, the reason for natural gas used as a home heating source. Another type of reaction is a solid state to the liquid state, so melting. So take an ice cube out of the freezer and you put it on the counter. And eventually it is going to yield liquid water when it gets to room temperature. You can also have a change of state from a liquid state to a gaseous state. Okay, so let's talk a moment about what are called functional groups. So these are groups of atoms that are associated with reactive sites. And often in reactions, when you write them down, they're denoted as R because R can represent many different things. And again, they can be a wide range of groups, or in fact, they can be hydrogen. So in this reaction here, we have, so now I'm not showing the carbons, but we now have a carbon-carbon double bond, and instead of the hydrogens, or it could be hydrogens, but we have 4 different so-called R groups. And XY here is a reagent, and so it could be hydrogen if we were trying to hydrogenate. It could be bromine if we were trying to brominate, like I showed you on a previous slide, or it could be a salt, such as sodium chloride. And so here you see this reaction, what's happening is you go and you're basically adding here, so you end up breaking the double bond, and now you have a single bond where you're adding the X and the Y, and you're retaining your R groups. Here in this case, you're going from a triple bond to a double bond and adding the XY and keeping your 2 Rs. You can also have substitution reactions for reactive single bonds. So here again, this is, again, carbon here. We have 1 R group, 2 hydrogens, and a bromine. And now we're going to displace this. And so our X is going to join up with the bromine, and we're going to add Y to our carbon atom. Okay, so let's talk about some other functional groups that are important. So we have amides, amino acids, and proteins. Okay, and we're going to talk about all of these. Okay, so amides are, I mentioned this before, the building blocks of proteins. And proteins are one of the 2 major classes of biomolecules. The other major class are what are called nucleic acids, and we'll see those a little later. Here, the CN bond, because carbon also happens to be doubly bonded to oxygen, gains, this is a single bond, but it gains additional strength from this double bond here. And it turns out that to try to break this bond is actually really tough. And so you have to treat it to really harsh conditions in order to do that. Okay, well, there are so-called 20 natural amino acids, and so I'll show you why I'm bringing this on with amides here. So amino acids look like this. So again, you have your carbon in the center, doubly bonded to an oxygen, and now here you have a hydroxyl group. This has a carbon, and there's an R, so R is one of 20 different things, and then there's an amine on the end. Okay, and so what happens with amino acids to make them peptides or full proteins is that you join them together, you stitch them together, and you can do this in the lab, but also it's done in nature, and we'll talk about that in a little bit. So here I have one amino acid coming in, you see it's R group, and you have another amino acid, and so what's gonna happen is this is where a reaction is gonna take place. And now I'm going to end up making the carbon-nitrogen bond here, so the amide bond. And now I'm going to have two amino acids stitched together, and I'm going to liberate some water from this reaction. So I'm liberating the OH and the H from here. And so you can keep doing this, and you create longer and longer and longer what are called peptides, and ultimately peptides become proteins. Okay, and so proteins, just like small molecules, do have some shape. So when we draw proteins, we like to draw them like a string of pearls where, the string is basically the amide bonds that are connecting them, and then the different pearls are the R groups. But in fact, because the R groups can be different, they can be large rings, they can be long chains, they can have charge, etc. They have different structures that they will adopt because that. And so you can have an alpha helix where they actually end up coiling and then interacting, and we'll talk about non-covalently, in between. Or you can have sheets. These are called beta sheets, and they're just formed in repeating patterns. Proteins will take on a three-dimensional structure, again, just like we talked about where we went from the two-dimensional drawing of the small molecule to the stick figures to the space-filling figures. Well, proteins do that too. And so, they're not just hanging out like that. They fold over each other, and they take these really interesting shapes. And the shapes happen often to end up signaling what activities the proteins are going to do. Okay, and then finally, I mentioned nucleic acids as the other major category of biomolecules. Nucleic acids are the building blocks of DNA and RNA. And so here's the basic structure of a nucleic acid. So you have a sugar here. So a sugar is just a carbon ring structure with an oxygen in it. In this case, it's a 5-membered ring structure. Off of that is a hydroxyl in what they call the 3' position. And up here, off of this position, is a phosphate group off of the so-called 5 position. And then off of the 1 position is some sort of functional group R that is a heterocycle. And so R, there are 4 of them. So you can have adenine, and this is where it's connected. You can have cytosine, guanine, and thymine, or in the case of RNA, uracil. And the only difference between uracil and thymine is that this isn't a methyl group, it's a hydrogen. But just like proteins, these guys end up building and building and building on each other. And so you can see here, what will end up being a nucleic acid string. So you have, one of your bases here. Now you're connected. Here's a different one. Here's a different one and a different one. And just like proteins, DNA and RNA do in fact form very interesting structures. And so, of course, I'm sure everybody's familiar with the so-called double helix structure of DNA. It's shown diagrammatically here. RNA takes many different structures. Again, you see the helical structures here. Proteins we've already talked about and how they can form coils and then coils of coils. So the question is, what do these biomolecules do? And for a long time, it was hypothesized, but now it's known through a lot of really neat science, a lot of which ended up winning different Nobel Prizes in chemistry. So what's known is that DNA transmits messages to RNA. And RNA transmits messages that ultimately make proteins. And proteins then can make small molecules. They make them as defensins, they make them as nutrients, etc. And so that's sort of the circle of life. Small molecules, again, organic molecules used to be those natural molecules that were found, in life, in organs, and they, again, small molecules. But again, we can now make those in the lab as well. But that's where the inspiration comes from. So when you hear the term natural product, that's because a protein has made it. Okay, so just a little more about, again, then what these machineries do to make proteins. So the machine that makes a protein is called the ribosome. This is a horribly lowbrow cartoon structure of the ribosome. The ribosome is machinery. It is in every living cell, bacterial cells as well. And the machinery consists of a large so-called subunit and a small subunit. Both of these subunits are basically mostly RNA, and they're held together by proteins, almost like jewelry. And so they're these very large structures. The role of the small unit is to take the message. So again, remember, the DNA gives information to RNA, and it takes this message, and the message says, hey, here's the amino acid that I want to put on, I'm making a protein here. Here's my first amino acid, and then I'm going to bring in a second one, and we're going to connect them, and a third one, and a fourth one, until I'm done, until I know the protein that I want to make. And then I'm going to send a stop signal, and then that process is going to stop. And then the ribosome, which is the thing that is housing this whole experiment, ends up protecting it and moving it along its way till it goes out in the world and becomes a new protein. And so that was a cartoon, but I'm going to show you now a video. And this is a video. So let's see, what was it? 2009, the Nobel Prize in Chemistry was awarded to some mentors of mine at Yale, Tom Steitz and Peter Moore, and then also two other ribosome researchers. And the Nobel Prize was awarded for their elucidating at the atomic level what this ribosome looked like. And once you saw that, you could then solve different structures using probe molecules that could show you exactly how the ribosome makes proteins. So this is a series of very beautiful structures and, again, very complex, heroic technology there. But the point is, it showed how these molecules provide an environment for proteins to be made. And so they strung all of these different structures, these were done by X-ray crystallography, into a movie. And I'm going to show you that movie now. So you can see, what's going to happen here. So you're going to see the big ribosome. You're going to zoom in to the site where the proteins are going to be made, and then you're going to see, one element that the ribosome calls in, which is so-called a tRNA. It's going to have an amino acid on it. You're going to see another one come in, and then they're going to do a reaction. This guy's going to go away. He's going to have the beginning of the polypeptide. Another one's going to come in. They're going to do a reaction. They're going to add and add and add. It's really a beautiful movie, and it happens also to be accompanied by some kind of fun music. So without further ado, I'm going to see if this works here. Oops, okay, and apparently I was watching this earlier, so let me go back to the beginning. Okay.
Erin, we can't see the video.
Oh, you can't see the video? Oh, darn. Okay, trust me. It was a great video.
If you,
Can I do something with my sharing?
yeah, I think if you share your YouTube
Okay.
instead of this, go ahead and try that.
All right. Okay. Did you hear the music?
Yeah, I did hear the music.
Yes. Oh, hold on.
It was very dramatic.
Yeah, it was very dramatic. It's more dramatic when you can see what I'm doing here. Oh wait. Okay. Oh, share my screen. Okay. Things were just going so well.
No worries. We've had bigger issues than this. This is nothing. We can do this. There it is.
Okay, so can you see this?
Yes.
Oh, awesome. Okay.
Try playing it. There you go.
Okay.
All right, I'm going away.
All right, thank you.
We lost the sound.
Oh, you did?
Yeah.
Oh, I don't know what to do about that.
Yeah. What we'll do is we'll post the video later.
Okay. But so you can see then what's happening here is this is the incoming amino acid. You're going to see a reaction take place here
Yeah, we
in
can.
a moment. Now we're going into the reaction. So it's too bad Handel's Messiah is playing just now because the bond was made.
Can you hum?
And now you're going to transfer over the amino acid to the growing chain.
Hallelujah. Sorry.
And now this guy is going to go away. And then a new one will eventually come in and the process will continue. And he's leaving. This is fiction. They don't really know how this happens, but okay. And that's the salient points of this. So now I will go back to, how do I unshare that? Drats, I really don't know the answer.
We can put
What's that?
Click stop sharing.
Oh, yeah, there you go. Okay.
Then go back to the PowerPoint.
Let's go back to the PowerPoint. Okay, well, I'm sorry. That is a great movie when it actually works. So we'll share that later. Okay, so then in the remaining moments, I thought I would be done like, half hour ago, but clearly I'm not. So we talked about how molecules react. Let's talk about how molecules interact, because that's going to be a lot of where we spend our time next week. So molecules or compounds can actually form complexes. And these complexes are two or more molecules. They're held together by what are called non-covalent or non-bonded interactions. So everything we've talked about before was making a bond. But these are just, you can almost call them attractions, affiliations, something like that, often described as binding. And they require a strong shape complementarity, and they can be driven by a hydrophobic effect, sort of meaning, like in this case, This is not, an embryo. This is meant to be a terrible schematic of a binding site, like a protein, like a drug target. And then this red thing would be like a small molecule that is going to want to get in there and bind. But they're both in this milieu, which in this case is probably water. And if this is a molecule that's kind of hydrophobic, so not, really liking water, it's going to want to get in there because it's rather be in a place where it's shielded from all of that polarity and enjoy some interactions. And so, this is, again, what are called complexes, non-covalent binding. And, this is seen in many different arenas, but certainly when you talk about designing drugs to target proteins or other targets in the body to affect some medicinal change, that's what we're going to be talking about. So the main types of non-covalent interactions, also electrostatic. So again, you can have really almost ionic interactions, but you can have things that aren't full charges. And this can be driven by something that's called electronegativity. So what do I mean by that? Okay, let's think of something like nitrogen and oxygen. Okay, so one is more electropositive and one is more electronegative. And so they'll kind of cheat and share. So they'll form this interaction, but they're not necessarily going to bind. And so these can form liquids, and it can have a dramatic impact on some of the properties of the liquids. A big one that we're going to talk a lot about are hydrogen bonding interactions. Again, this is another type of electrostatic interactions, but in this case, you have X that's bonded to an H, okay? So X could be nitrogen or oxygen, maybe even sulfur. But this H is going to participate in a hydrogen bond with Y, where Y is another one of these so-called heteroatoms, nitrogen, oxygen, sulfur. And the reason that this can happen is because both NH bonds and OH bonds are polarized. Okay, so there's a strong negative charge on the nitrogen or an oxygen and a strong positive charge on the hydrogen. And that sort of stretches them out and allows for this diffuse sharing of electrons, if you will. Now, these interactions are nowhere near as strong as a bond. They're about 10 times less strong, but they do provide for some very interesting structures. Now, to make an ideal hydrogen bond, there's both a distance and an angle, so an approach to the electrons that make for ideal interactions. These can produce some very interesting structures. So water molecules, the individual little water molecules, actually form very interesting networks of hydrogen bonds. And this is a key reason why water molecules, for the little size, have pretty high melting point and boiling point. Methane molecules can't hydrogen bond, okay? And so they have a significantly lower melting and boiling point than water. So again, it's about these higher order structures that you can achieve. And then the other type of interactions are van der Waals interactions. And these are sort of more non-polar, almost, I would say, sort of shape type interactions. Again, we're going to talk a lot about this next week. And just to think about it graphically, these can be thought of as sort of host-guest interactions, okay? So they're not bonded, but they're enjoying some time together. And there are many different applications of these kinds of complexes. Again, drug design I've mentioned, and we'll talk about that next week. Drug deliveries. So some drugs, are terribly soluble, so they can't be delivered as oral agents by themselves. But there are these cage molecules. Some of them are called, for instance, cyclodextrins. And the purpose of them is to just attract the guest molecule in them and sort of shade it or protect it until it gets to an environment where it wants to be, and then it moves out because now the attraction is stronger to a tissue, for instance, than it is to body fluid. Chemical sensing and also environmental applications. So, taking carcinogens out of well water, for instance, and also superconductivity. So a lot of different applications of non-covalent bonds and the role of host-guest complexes in that. So again, we're going to talk a lot about this next week. I am done. I hope this was somewhat useful, and I'm happy to take not very hard questions, and certainly we'll be happy to share that video and anything else that you'd like to have. So thanks a lot for your time.
Hey, thanks, Erin. Excellent. Can you hear me, or do I have my mute on?
I can hear you.
Okay, good. We have some questions. I'm going to go back to the very beginning, and we're going to scroll downward. Let's start at the beginning. Let's see. A lot of comments. Where's our first question? Here's one from Mary Ellen.
That's not a question, that's a comment.
It is. Actually, one of the things we had tonight was a lot of comedy, like a lot of funny science jokes. And we're going to probably pick a winner. You're going to pick a winner among those for your books. We're going to do the drawing for the pint glass, but I want you to see these jokes because they're hilarious.
Okay.
But anyway, let's get to the question. Okay, well, here's another comment from Mary Ellen before we get to that.
C and C, not carbon and silicon.
Right. See, I'm having a hard time getting through all the jokes here. Okay, here we go.
Okay.
Mary Ellen again.
Oh, that's an excellent question. I mean, that gets to the heart of it. I think the cosmeceutical world, as I've come to know it, there are some really good products out there. I mean, a really good example, not that I would know anything about it, but Botox, is it's obviously a neurotoxin, but applied topically can be useful, obviously, for reducing wrinkles, fine lines, but more recently, and I think much more interestingly, has been used for migraines. There are a lot of drugs, small molecule drugs that have been developed to treat migraines, and not particularly successfully, or certainly not successfully for large groups of people. But they discovered that small injections of Botox can have a pretty dramatic effect on that. And so that's a great example. A lot of these potions and lotions, you probably have to be a little careful with. So I think it's a real mix. And I think, just like we were talking last week, if there are data that are published in peer review for these, and there are journals that do publish this, then that would be the place to feel comfortable. And then also the package insert to understand, what the true benefits are.
Here's another one.
Well, yeah. So, so the word saturated literally means, the single bonds. I should have said that. And unsaturated are double bonds. And so again, these have impact on structure. And in terms of fats, then also have an impact on their properties, just like I showed with the carbon and hydrogen example. So it's that same thing. It's just the bonding characteristics that lead to different performance characteristics or molecular properties.
Here's a question from someone you know, maybe.
Well, so we were using atoms to make molecules to bind to different targets on bacteria to render them ineffective. Now, these were mainly, they would be powders that we would make, but often you would need to solubilize them, in some liquid in order to deliver them as a drug.
Okay, how about this?
So good. It's the same thing, so this, I mentioned it, but this hydrophobic effect. So When you have, a long polypeptide, again, because the amino acids have shape and charge themselves, then, it's just like I talked about how molecules can interact. So they like to interact. And so you'll find, for instance, ammonia. So one of the amino acids is lysine, which is terminated with an ammonia or an ammonium group if it's charged. Ammonias like very much to do what they call cation pi interactions. So there are other amino acids that are aromatic. So it's a pi system. And so they'll want to figure out how to get next to each other to do that. And it's often really driven also by some of these things don't like to be hanging out in solvents. They want to try to hide themselves, I guess we used to learn this term, likes dissolve like. So let me get in an environment that I feel more comfortable and then engage in interactions, with those things around me.
All right, here's another question.
Well, I can't remember the topic, but so I was trained as a computational chemist where my entire focus was on how molecules interact. And so at the time, so you got to roll the clock back, we were almost using abacus at that point. It was that early in computer science, but we would look at how how proteins come together, how small molecules bind to proteins, what are the reasons they interact? Can we quantify that? Can we match that to experiment? Can we then use that information to design molecules to do it better? So very much setting me up for what ultimately was what I did in industry, which was to design drugs.
I have a copy of your thesis upstairs. I may read it after this.
Yeah, I'm thinking that's probably not a great idea.
Here's another question.
Well, I think, for me, I got into chemistry because I liked math. And we did no math tonight. And when you get to physics, I can't wait to see how Stacy Vargas is going to do physics without math on this. But anyway, there's a lot of math involved in this, and that sort of attracted me. But then really understanding how molecules interact and react and their impact on everything. You think about, there's not a thing that chemistry isn't at the heart of. And I hope I showed you that today. It all starts with the atom. And so for me, it's just a lifelong discovery of how molecules behave. So it's with a lot of force. So, good question. How are man-made elements made? It's with severe chemical methods to pump more electrons in, to a system.
Okay. A lot of good comments coming in. And
thank you, Mary Ellen.
So, let's see. This is not really a question, it's more of a rhetorical comment.
Kind. Well, honestly, isn't that part of it is making it engaging?
Oh, look.
Absolutely.
Let's get back
Albert.
Albert, because he's never commented on any program I've ever done before, but here he is, my friend Albert Vargas, who is married to one of our presenters. You'll see.
That's right.
Here's that.
I did want to, so in fact, that's what I did for part of my living. It didn't used to be called AI. It just was called computational chemistry. But you're right. Now that computers are so fast, this little computer that I'm talking to you on is faster than anything I did my thesis on. And, through the cloud, people are allowing outfits to run reactions at night. And so you can, look at these proteins and you use a technique called molecular dynamics, which allows them, to move and you watch, again, based on thermodynamic principles, how they fold and interact and what those favorable orientations and conformations are. And yeah, you're seeing more and more of this because it's cheap and people kind of like the fact that their machine's running at night doing something maybe good.
Okay, here's one. I don't know if it's meant to be a joke, but it's funny because it's kind of a nerd question.
Yeah, I might.
I get it.
Yeah, those things you don't throw out. Thank you.
There's Diane. She says hi.
And that's not true. But anyway.
Not true at all.
Yeah, boy, Bonnie, I'm with you. I mean, I pulled out my periodic table from my chemistry days, and then I went and looked at the periodic table today, and I was, yeah, I was a little shocked at how much it's grown.
Okay.
Great. Okay, so who's the winner?
We're going to draw for the beer pint first.
Okay, first.
And you're going to pick the funniest chemistry joke. Okay, here we go. I'm drawing right here from my hat. There were probably, I would say, 30 entries. I don't know, something like that. You know who won? Albert Vargas.
All right, Albert.
He qualifies because even though his wife is a teacher, he had nothing to do with this. So, all right, Albert, you won the beer pint. Congratulations. You and I will have to toast to that at some point. All right. Let me show you some of these jokes before we go because they're hilarious. First, this one.
That's pretty good.
Oh, they get better. Here's another one. Oh, well, I won't say this is one of my favorites, but it is. Okay, here's a good one.
Okay, Gino's got some good ones.
I like this one too.
That's pretty cute.
Here's one from Janet, my old friend Janet. She's not old. Our friendship is old because, well, okay, we're old.
That's pretty cute.
Okay. Is there any more? Let me see.
Well, Mary Ellen had a few.
Yeah, Mary Ellen's were good. So I don't know. Is it fair to ask you to pick one?
No, it's really not fair.
Okay, I'll just draw another one then.
Yeah, draw another one, but those were all good.
Oh, look, from Alicia. Hi, Erin.
Hey, Lish.
Okay. You know what? Liam is a 9-year-old watching the program tonight. I'm putting he's in the drawing. Let's draw another name. Here's Hope's joke. That's pretty good. Who knew that people who love science could also be funny? I mean, that's pretty good. All right, here we go. We're drawing a winner for your books, Erin. Which are really nice. And the winner is Erica Donahue, which means Liam.
Liam.
Yes, indeed. Congratulations, Erica, Liam, and Fiona, and everyone who watched tonight. Yeah, Janet says give. I actually drew fairly, and he won them. So there we go. No controversy here. All right. Thanks, everyone. And remember, next week, Erin's going to talk about antibiotic resistant bacteria, which is a very important subject. Do not miss that one. That's what she does for a living. Here's another comment from Bonnie before we go. Yes, Bonnie, he won. Don't scold me. Yay, Liam. Everyone's happy. Okay. All right. Great.
Thanks, everybody.
Okay.
Okay.
Erin, thank you.
Thank you.
We'll see
Bye.
you. Bye, everyone.